Okay, so today we are going to see one experiment, or you may say one simple problem with a bar, and this bar is having a load of 10,000 Newton at one end, and it is having a cross section of 225 cross 225 mm and length of 3048 mm. The material property is 210 GPa and Poisson ratio is 0.3. It's a simple case of a bar with a tensile load at one end. So we are going to model this one on AutoCAD or SolidWorks, and you may also do the same thing on the design modeler, which is available in ANSYS Workbench. So when I'm going to click on the design modeler, so you can see on this one when I'm going to drag a new static structure analysis like this here at the viewport, and then I'm going to right click on it, and then I'm going to select the new design modeler. So this will going to open this design modeler will going to open, and I can create the sketch, and then I'm going to use the extrude command, and then I can get this particular body. So you can see this, it is having a length of 3048 mm length, and it is having a cross section of 225 cross 225. So I'm going to import this model um, from either from AutoCAD or SolidWorks, or I can make this thing here itself. So by doing this, after that I am going to send it to the model setup in the static structure analysis. So I'm going to double click it, and I'm going to click edit. So after doing that, I will going to have this thing open up like this. Now, I'm going to define the material property here. So I'm going to click on the solid body on the left hand side in the tree, and then I'm going to select the material assignment. In the material assignment, you can see that I'm selecting structure steel here because I have defined 210 GPa. You may go for other materials also by selecting or giving the name here, and you can have different kind of other steels or materials you may choose for the different analysis. So after doing that, I am going to make the mesh. So I have selected the mesh here. So I have given the body size of 50 mm as a one single element. We're going to have the size of 50 mm each. So one element of quad. It is a small rectangular element, cuboid element here. Okay, hexahedral element it is, and this hexahedral element is having a size of 50 mm cross 50 cross 50. So by that I have made this particular element using for the mesh of this particular body. Now after that, I am going to click on the static structure analysis, and then I am going to click on the type of support I am going to give it. Thus I am having fixed support. I'm going to click fixed support. So after giving the fixed support, I am going to select the top face of this particular body, and I'm going to click apply. So this will be fixed as already shown in the diagram here. The top one is fixed. So and after that, then I'm going to select the force. So I'm going to click right click insert. In insert, I'm going to select force. Then I'm going to get force here, and when I'm going to select force, then I'm going to select the face on which I want to apply. So I want to put the force on this particular down space below face. Yes, I selected that. Then I have given the value equals to 10,000 Newton here on the table. Here on the table I have given 10,000 Newton. So the direction of the force is downwards. So as we have defined in the geometry, so accordingly we are going to do that, right? So this is the condition. We have defined the condition. Now after that, in the solution part, I am going to right click, and then I am going to insert. Then I'm going to go to the deformation, and then I'm going to select the total deformation. I'm going to say that how much deformation has been occurred in the body. So when I'm going to click this, this total deformation will going to come down. Now after this, the thermal condition I have given here for the body is 22 degrees Celsius. So I'm going to continue with 22 degrees Celsius here. I'm going to put the at the end of 1 second it is 22 degrees Celsius again, and then I'm going to click the solve button. So when I'm going to click the solve button, I'm going to get the result out of it, and I'm going to check with the simple formula, that is PL by AE, that what exactly it is coming. So without seeing the answer here, I'm just going to see the formulation. So if you are going to see the formulation, so you just put PL by AE and just calculate. So what it will going to come, it will going to come near about 0 point the value by putting the value of P, that is P is equals to, here we are having 10,000, L is equals to 3048, A is equals to 225 cross 225, and E is equals to 210 GPA. Okay, this is the value. So when you are going to put these values and you are going to calculate the value of del, the value it will be 0.00287 about approximately mm. Okay, it will be about 2877. Okay, to 0.002877 mm, right? So now let's see the result what we are getting. When I am going to see the result, the value will is about 0.003000. So the value what we have calculated is 0.00287 and the value what we are getting in the analysis is 0.003 mm. So it is near about same, and so we could say that the analysis and the calculation shows you the same. And by after doing this, when you are going to see the thing, one fact is that the body is at 22 degrees Celsius, right? So if I want to change the temperature, let's say suddenly the temperature rise up to 400 degrees Celsius. So I have placed 400 degrees Celsius, and then I am again going to solve this problem. So what will going to happen? The due to the rise in temperature, the Young's modulus will going to increase. The Young's modulus will going to decrease of the material, right? This material property will going to reduce. The rigidity will going to reduce. So due to that, the deformation should increase. So that is what we are going to check here. So when I'm going to click on the total deformation, you can see the total deformation what we are having is about 13.956. So initially it is 0.003 mm and now it is 13.33, 13.956 mm, right? So initially it is 13.956 divided by 0.003. So it is approximately 4,000 times, 4,600 times the uh, deformation has been increased due to the increase in temperature. So what you have to take care about is that whenever the material is subjected to temperature, you have to take care about the change in Young's modulus with respect to temperature. So this states that whenever a metal is subjected to temperature, the Young's modulus reduces. So due to that, whenever we are designing a component and there is an application of temperature, you should take care about the deformation occurred due to the rise in temperature. So this is a simple example of an FEM analysis of a bar. So by that you could understand that why there is a failure of structure when 9/11 incident has been happened and the whole building used to collapse. It is because due to high temperature, the metal can't come in contact with that high temperature has gone through a serious reduction in the Young's modulus. So as per se, the Young's modulus of steel at 22 degrees Celsius is about 210 GPa, and at approximately 900 degrees Celsius, the same Young's modulus reduces to 70 GPa. So due to that, the whole structure was actually collapsed. It is one of the theory behind the collapse of the structure. So let it be. We are going to have more numericals. We are going to have more numericals on this, and more. We are going to have more examples on this. So accordingly, we are going to move. Thank you, guys.